Hey, this is Mrs. KJ going over part 2 of 4.12 Covalent Bonded Molecules. The last recording was so short because my headphones shorted out and then it wouldn't let me fix anything, so that's why that one was short, and we'll just continue on here. Many gases consist of two covalently bonded atoms. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine are elements that occur in nature as diatomic molecules. All right, what does di mean? Two. So two atoms in a molecule. What are molecules? They're covalently bonded together. So in other words, you've probably noticed in equations we always have Cl2 or O2 or H2. We never have one of these elements by themselves because it's just never going to happen. They both want full outer shells so badly that they will always bond with another one of itself if there's nothing else available. So like the chlorine, they each want to gain one valence electron, therefore they share. It's just straightforward as that. They want it so badly that they'd rather share than be alone. So dichloride, two chlorine molecules. These molecules are formed through covalent bonding between two atoms of the same element. By sharing one or more electron pairs between the atoms, these elements can have a full outer shell, a full complement of electrons in their outer shells. The resulting diatomic molecules are more stable than a single atom. For example, chlorine has 7 electrons in its outer shell. If each of two chlorine atoms shares 1 electron with the other atom, then each atom fills its outer shell and it is stable. The shared pair forms a covalent bond between them. The result is that chlorine normally is found as the diatomic gas molecule Cl2. Atoms that bond covalently form molecules. Most nonmetals bond covalently with each other to form electrically neutral chemical compounds called molecules. Consider the gases methane, CH4, ethane, C2H6, propane, C3H8, and butane, C4H12, all of which can be burned for fuel. Each consists of carbon atoms covalently bonded to each other and to hydrogen atoms. These are all molecules because they're covalent. Unlike ions, molecules do not break apart or dissociate when dissolved in water. So, methane, ethane, propane, butane. Atoms within a molecule can have more than one covalent bond. Atoms within a molecule can have more than one covalent bond. For example, the natural gas methane, CH4, has one carbon atom bound to 4 hydrogen atoms. Each carbon-hydrogen bond is a single covalent bond. Each hydrogen atom forms a single bond with the carbon, but the carbon atom has 4 such bonds. All right, so here's hydrogen. It's going to form a bond here. So this is 1 of carbon's bonds, 2 of carbon's bonds, 3 of carbon's bonds, 4 of carbon's bonds. So carbon can form a total of 4 bonds, and in this case it does with 4 hydrogens. Carbon dioxide, CO2, the gas that you exhale, each oxygen atom shares 2 pairs of electrons, a total of 4 electrons with the carbon atom. The carbon atom has a double bond to each oxygen atom. A double bond means that 2 pairs of electrons, 4 electrons altogether, are shared. So this is a double bond. This one is dioxide, I should say dioxide, O2. And here we can also see that we can have a triple bond. So let me go ahead and draw you a picture of CO2. So we're going to start, we have 1 carbon and how many oxygens? 2. And then we want to do our Lewis dot diagrams. And so for our Lewis dot diagrams, carbon is in group 4. So how many valence electrons will carbon have? 4. Now oxygen is in group 6. So how many valence electrons does each oxygen have? 6. And how many total valence electrons does oxygen want? Well, it wants a total of 8. And what about carbon? How many valence electrons does carbon want? It also wants 8. So what's going to happen here is sharing. All right, so let's do this first. you can probably see pretty easily that these two electrons are going to get shared, right? They're right next to each other, they're going to get shared. If oxygen is sharing with carbon and has one bond, how many total valence electrons does this oxygen currently have? 1, 2, 3, 4, 5, 6, 7. Is it happy? Does it have a full outer shell? No. So what's going to happen is this electron's going to scoot over there, and this electron's going to scoot over here. And what do you think is going to happen next with those two electrons? They're simply going to form another bond. And so now we have a double bond. We have two pairs of electrons. We have a double bond. How many valence electrons does this oxygen currently have? 1, 2, 3, 4, 5, 6, 7, 8. All right, what about carbon? Well, let's start on top. 1, 2, 3, 4, 5, 6. All right, so obviously it's going to bond with the oxygen here. So now let's count how many valence electrons does carbon have? 1, 2, 3, 4, 5, 6, 7. So what does it need to do now? Well, we have to keep sharing, right? We got to share some more. So this electron is going to move over here. And this electron, which I drew really big, sorry, is going to come over there. And what are they going to do? They're going to form a bond. And now we can see that carbon has two bonds around it. So if I rewrite this a little neater here, because I know it kind of got messy, there's two bonds, a double bond between each oxygen and carbon. And oxygen also has 4 valence electrons around it. And now you can see carbon has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Now I just drew them as straight lines, which is all you have to draw them on as. Like here, it's a straight line, and we assume that everyone knows it's a pair of electrons. All right, now here they drew it with the orbitals to show you better that, oh yeah, it can zip around either of the two atoms. And here with a triple bond would be something like dinitride. So nitrogen is in group 5. So if it's in group 5, how many valence electrons does it have? It has 5. So it has 5 valence electrons. And I would draw them all around like this. And it's going to share with its neighboring nitrogen. And it's going to share enough so that they both have a full outer shell. So normally I would draw the other two electrons here and here, but I'm going to save myself a little bit of time. And I'm just going to draw them in here. And I know that these two electrons are going to zip over here. And when they do that, we are going to have what kind of bonds in between them? We are going to have a triple bond because these electrons are shared, these are shared, these are shared. So nitrogen would have a triple bond. Atoms can form as many as 4 covalent bonds with each other. Okay, so for example, we showed carbon here. It has the 1, 2, 3, 4 bonds. It can form up to 4, but you never have a quadruple bond. The most you can have between two atoms is a triple. But you can have 4 altogether when you're counting all the way around the atom. Welder's gas, oxyacetylene, C2H2, consists of 2 carbon atoms and 2 hydrogen atoms. Each carbon atom shares 3 electron pairs with the other carbon atom. Okay, so we have a triple bond here. And 1 electron pair with each hydrogen atom. The carbon atoms are triple bonded to each other, while 1 hydrogen atom is single bonded to each of the carbons. A triple bond means that 3 pairs of electrons, 6 electrons altogether, are shared. Covalent bonds give various properties to covalent compounds. Covalent bonds are strong bonds that hold molecules together. Covalent compounds have chemical properties that are different than those of ionic compounds. Covalent compounds can be gases, liquids, or solids at room temperature. Most ionic compounds are solids. They can have a low melting point and low boiling points compared to ionic compounds. So when we think of covalent compounds, you should be thinking of what? Water and carbon dioxide. Those are your two best examples. Water and carbon dioxide. So you can tell, oh yeah, we have liquid normally, but we can freeze, we can melt it pretty easily. And carbon dioxide, yes, is the gas, but when we get to naming, I'll explain why that's such a good example. Covalent compounds are often soluble in water and nonpolar solvents, while ionic compounds typically dissolve only in water. Covalent compounds are poor electrical conductors regardless of their state, while ionic compounds are poor conductors in the solid state, remember when they're in that rigid crystal lattice, but they're better conductors when melted and excellent conductors when dissolved in water. Why? Because of those positive and negative charges. These are the rules for naming covalent or molecular compounds. When you see a formula for a compound, first look at the atoms that are in the compound. For example, take N2S3. You can see from the formula that the molecule contains nitrogen and sulfur. The first thing you want to do, decide if it's ionic or covalent. Okay, well obviously this one's covalent because the lesson is covalent, but two nonmetals, okay, covalent. Remember, if you're doing ionic compounds, that's a metal and a nonmetal, like NaCl, all you have to do to name those is change the ending to "-ide". Unless it's a polyatomic ion, then you just write the name. All right, when you're naming ionic compounds, it's pretty easy. Covalent compounds have a few more steps. You still change the ending to "-ide", but we have a few extras along the way. Number 1, list the element names in order of increasing group numbers. So you go from left to right. So nitrogen would come before sulfur. Add prefixes to show how many atoms of each element are present. The chemical formula shows that there are 2 nitrogen atoms and 3 sulfur atoms. Using prefixes gives dinitrogen trisulfur. If the prefix ends with a vowel and a root begins with one, like oxygen, drop the vowel from the prefix. So tetraoxide is really tetroxide. So we dropped the A because it was a double vowel and the A was part of the prefix. And then add the suffix "-ide" to the root of the second element. So sulfur needs to end in "-ide", becoming sulfide. So the name of N2S3 then is dinitrogen trisulfide. Sometimes to avoid ambiguity, did you get that? Sometimes to avoid ambiguity, mono is applied to the suffix. For example, carbon monoxide. Okay, I don't like how they said this. Really, you always add mono to the second element, you never add it to the first one. All right, so rules for naming. Given the compound DXJY, is dihydrogen? Yes, it's an acid. No. Are there more than 2 elements? Yes. Well, then you have a polyatomic. So you're going to have an ite or an ate. And you can keep going on here. I'm going to pause reading this. If you like this diagram so far, hit pause and I want you to finish reading it. If you're reading this diagram and you're like zoned out or you're like, wait, what? Then skip it. This is one of these things that some people get really well, some people don't. So hit pause and read it, look at it. If it helps you, great. If not, we have other ways to help. If you haven't, go into your cheat sheets and download this. It has the rules for naming ionic compounds. You can use this on all tests and quizzes. And it says, step 1, write the element's first name. If there's more than one atom of that element, add a prefix. The prefixes are listed down below. Step 2, write the second element and always add a prefix showing how many atoms of that element are present. Also change the ending to "-ide". So we have dinitrogen monoxide. Nitrogen dioxide. Remember, the first element never gets mono, but it does get the other prefixes if there's more than one atom. Naming takes practice. Go back to the content. There are some worksheets here that I put on. You have to practice naming. It's the only way to get them. You'll also notice there's 2 quizzes. This quiz has questions where there's nothing to do with naming. This quiz is only naming. So if you feel ready right now, take the no naming quiz. Practice naming before you take the naming quiz. And I have one more slide to go over. My timer's going to run out, so make sure you hit pause and read through all this. Nonmetals share valence electrons from covalent bonds. You can have a single, double, or triple bond, but each atom can have up to 4 bonds, and they produce unique properties in covalent compounds.